Alright, so let's talk about how can we do the representation learning of the nodes in the graph with this encoder based on transformers, and how can we do the further pre-training and fine-tuning of the Graph-Bert with some task. So before we have mentioned that given the input graph, we can sample some subgraphs for each target node right out, and we can also define their initial embedding vectors with both the row features as well as the position information. So formally, we can define the initial embeddings of all the nodes in the input graph subgraph as H0 we define here. So this H vector that we define here covers all the information for each node in the input graph. Now this HI0 denoting the initial embedding vector for the target node, covering the row features as well as the position information. By summing all the initial embedding together, we can define this H vector we show here for all the nodes in the input subgraph. And we further organize all the initial embedding for all the nodes in the subgraph together into this H matrix as we define here for the inputs for the encoders. Then how can we define the encoders? So we define this encoder by the combined transformer with the gResonate. So we do the representation learning of all the nodes in the input subgraph layer by layer. And for the else layer, we can learn its embedding vector as HA as we show here, right? It will be, it receives its HA minus 1 as input with one layer. In each layer, we have both the transformer, which is in this term, combined with gResonate term and this term as we show here, right? I hope you still remember how can we define this term, right, for transformers, and what is the physical meaning of this term. Through the gResonate, it captures the residual learning terms, among different layers for the graph input. And we define the gResonate term with different terms, either naive one, or graph naive, or graph raw as we defined before. So by summing them together, we can define the embedding vector we can learn for the else layer of all the nodes in the subgraph. So we mentioned that we can do the representation learning layer by layer iteratively. So to show you the learning process, we also illustrated the process with the formula we define here. So based on all the initial embedding for all the nodes in the subgraph, we can define the H0 as the input for the encoder. And with this graph transformer as the encoder, we can learn the embedding vector for all the nodes in the graph or in the subgraph layer by layer iteratively. And we can illustrate the iterative updating process of the embedding vectors as by the formula we show here, right? And for the output of the last layer, this layer, the D denotes the depth for the model architecture. So for the output of the this layer, we can further fuse them representation together for define the final embedding vector for the target node. You may wonder why we have to fuse here. The main reason is because we sum a subgraph for the target node, for one single target node, right? And all the remaining nodes, they are the learning contexts, right, of the target node. So by fusing all the representation learning of the target node together with the context nodes, then we'll be able to capture more comprehensive information for the target node, from the sample subgraph. So therefore, we further fuse all the nodes representation learning in this H matrix of the last layer to fuse them together to define the final embedding vector for the target node by the term we show here, which is the EI as we show here, right? So how can we define this fusion, this function? We can define this fusion as the average of all the involved nodes in the subgraphs based on their embedding vectors. So this is for one single node, not ZI, right? In a similar way, we can learn all the nodes embedding vectors in the input graph by following a similar process. So for all the nodes VI in the input graph, we can learn its embedding vector by the model as ZI as we show here, which will be further served as input for downstream application tasks to be started later. So this is the process we learn the embedding vectors for the nodes in the graph via the pipeline. So based on the embedding vector for the nodes, we can further start some tasks, for pre-training and for fine-tuning. So in the Graph-Bert, we start two unsupervised pre-training tasks. One is to start the row feature attribute reconstruction based on the embedding vectors. So given the ZI vector embedding vector for all the nodes, we can further reconstruct the row features, right, which is X hat via some model like MLP, and then we can further minimize loss function between the reconstructed features compared with original ones to define loss function. At the same time, based on embedding vector among of all the nodes in the graph, and we also define their intermediate scores among each other, right? We can define this one as S hat as we show here. So by comparing this S hat with S matrix we defined before, we can further reconstruct these original structures of the whole graph instead, right? So this two tasks doesn't require any supervision information, so they are both the unsupervised pre-training tasks, for the Graph-Bert pre-training. And based on pre-trained Graph-Bert, we can further transfer them for starting some other applications via transfer learning, also with fine-tuning as well. So we start two other fine-tuning tasks. One is for the node classification, one is for the graph clustering. So based on embedding vectors of all the nodes, learned by the pre-trained Graph-Bert, we can further feed them to some models for inferring labels of the nodes as denoted by the y-hat, and we can define the loss function based on constant entropy for all the nodes in the training set to fine-tune the model again. Similar for the clustering, based on embedding vector of all the nodes, we can further feed them to the some function for clustering the graph into different clusters. Okay, so this is the way how this Graph-Bert can work, with a puppet 9. So let's go over the architecture again of the Graph-Bert. So given the original input graph, we can do a sampling of some subgraphs from it. So the subgraph will sample for each of the nodes at the target node. The main reason we do the sampling is because, if the graph data is very large, then the learning on the whole graph will be inefficient. We do the sampling to learn based on the subgraph instead, which will be much faster. Also, the subgraph allows us to do parallel learning of the model. So for all the nodes in the subgraph, we can further calculate the initial embedding vectors covering both the row features as well as the position embedding vectors of the nodes. So we sum all the initial embedding vectors together, feed them to the encoder for learning their representations layer by layer. And based on the representation of the last layer, and we can further feed them to the fusion component for learning embedding vector for target node and as ZI, as we show here. And this ZI will be the embedding vector we learn for each node in the graph. And the ZI vector can also be serving as inputs for some functional components for classification of the nodes, for clustering of the nodes. Okay, so you can go over this architecture again by yourself by reading the paper we provide with in the schedule spreadsheet on Graph-Bert to get more information. Okay, let's do a quick summary for this part. So in this part, we talk about two models. The first one is GResNet, and second one is called Graph-Bert, right? So we start this section by talking about a very important problem we observe for learning deeper GL models, which is called suspended animation problem. When it comes to a deeper GL models, there will be sufferings from the suspended animation problem, not because if we have multiple Markov chain layers on top of each other, they will converge all the embedding vector for all the nodes in the graph to the same representations, right? So to address this problem, we talk about the new model, which is called GResNet, to combine the GL model architecture with graph-related learning terms. We discuss different terms can be used for building the GResNet, and also compare the different architectures and the performance, right? So besides GResNet, we also talk about another model, which is called Graph-Bert. So given the whole graph, we talk about how to do the sampling of subgraphs based on page rank, and we also discuss how can we do the embedding of row features as well as the position information, right? And based on this kind of components, we can further learn the embedding vectors via the Graph-Bert, via the graph transformer as an encoder. Then we can further fuse them together with the fusion component and also apply them to some downstream application tasks, right, for pre-training and for fine-tuning. So this is this part. And if you are interested in the GResNet and the Graph-Bert, please also check the papers we provide you in the schedule spreadsheet. Also a reminder, for the project 5, it will be due by this Friday midnight. So if you are interested in the source code for GResNet and the Graph-Bert, please also check these links for more information. Okay, so that's it for this section. Thanks for your attention. Bye-bye.